And welcome back for our last talk of the afternoon session. We are very happy to have Dylan Allegretti, who will tell us about the positive basis in skein algebras.
Okay, thanks a lot. And thanks very much to the organizers for inviting me here. So my topic is the categorification of skein algebras. And this is based on a very recent paper that just came out in the last month with Peng, Shan and Hyun Kim. So in the beginning of the talk, I'm going to explain what this is, what a skein algebra is. And to motivate the topic, I'm going to start with the notion of a character variety. So here I'm talking about character varieties of surfaces, and I will write SGN to mean an oriented surface of genus G with n boundary components. And I'll assume always that the Euler characteristic of this surface is negative. So that means 2 minus 2g minus n is less than 0. So given such a surface, we can talk about its character variety, which is some kind of moduli space. And here's the definition. So the SL2 character variety of this surface, let me abbreviate S for SGN. Then the SL2 character variety of such a surface is the following. It'll be denoted M flat of SL2 because one can think of this as a moduli space of flat connections, flat SL2 connections on the surface. But you can also understand this more concretely, so we can define it as by taking group homomorphisms from the fundamental group of S into SL2. That set of homomorphisms has the structure of an affine skein, and we'll consider the GIT quotient by the conjugation action of SL2. Okay, so let's try to understand this thing a little more concretely. This is an affine scheme, and so it suffices to describe its algebra of functions. So the algebra of regular functions on this character variety is generated by the following things. So we have a set of regular functions that I'll call trace gamma. And what this means is, so what is gamma? Gamma is referring to a homotopy class of loops, free homotopy class of loops on S. And what is the definition of this function? So if we take a point in here, which is given by a representation of the fundamental group, a homomorphism into SL2, then we just do the following. We evaluate this function on a point rho, and it gives us the trace of rho of gamma. So here rho is a point of the character variety given by a representation of the fundamental group of S into SL2. Okay, now I mentioned that we talk about surfaces with boundary, and in the case of a surface with boundary, it's very natural to modify this construction a little bit and look only at homomorphisms that that behave in a specified way for boundary components. So let me explain more precisely. So let's suppose that gamma 1 through gamma n are elements of the fundamental group, which are loops freely homotopic to the boundary components of the surface. Okay, so the surface has n boundary components, and these are the loops that go around the boundary components. Let's also choose the following data. So lambda will denote an n-tuple of non-zero complex numbers. And then given these things, we define the relative character variety as follows. It will be denoted like this. So similar to what I had before, I'll write m flat, but now with a lambda. So this will be a subspace, a subscheme of the character variety that I talked about previously. So this is defined to be the closed subscheme cut out by the following equations. So remember, we have these functions, trace gamma, on the character variety, and in particular, when the surface has boundary, we have these functions trace gamma I associated to boundary components. So we'll impose the relation that trace gamma I equals lambda I plus lambda I inverse, where I goes from 1 to n. So what this is saying is, so it's like you're fixing the conjugacy class of rho of gamma I for each boundary component, because this is like the sum of two eigenvalues of a matrix in SL2. So that's what the relative character variety is. And now I want to talk about skein algebras. What is that? So as I'll explain now, the skein algebra is a quantization of this space. Okay, so to define this, let me set up a bit of notation first. Let's write LA of S to mean the free module over this ring of Laurent polynomials in A. So it's the C adjoint A plus minus 1 module generated by isotopy classes of framed links in this 3-manifold S times the unit interval. So you imagine like knots and links living in that S times 0, 1, and these are considered up to isotopy of framed links. So they have the additional choice of a framing, which is a field of vectors that are transverse to the tangent vector of the link, and we consider these things up to isotopy. So this is the module that they generate. Yes, because these lambdas will actually have some significance later when I relate the skein algebra to something else. Thanks you for the question. So now, this is some module, but I can give it an algebra structure in the following way. So if L1 and L2 are framed links in S times 0, 1, then let's write L1 prime to mean the link that we get from L1 by applying an isotopy. So it's L1 isotoped to lie in this subspace S times the interval 0 to 1/2. So certainly you can always apply an isotopy to push any link into that part of the manifold. And similarly, let's write L2 prime for the link obtained from L2 by applying an isotopy so that it lies in this space, S times the interval from 1/2 to 1. So in that way, we get two disjoint links from L1 and L2, and we can get a product on this module, LA of S, as follows. So LA of S is generated by isotopy classes, so let's consider the isotopy classes of L1 and L2. And let's define their product like this. We'll take the isotopy class of the union of these modified links, L1 prime and L2 prime. So that gives an element of this module, LA of S, and this definition depends only on the isotopy classes of L1 and L2, so it defines, so it's well defined, and then extending bilinearly, we get a product. We get an algebra structure on this module. That's not exactly the algebra I want to consider, though. So we're going to do one more modification here. So we'll define now the Kaufman bracket skein algebra of S, and often I'll just call it the skein algebra. We define this as the following quotient. It'll be denoted SKA of S, and it's the quotient of LA of S by some relations, some skein relations. So these can be described in pictures. So here this disk here is meant to be some small neighborhood on the surface. And so this is just shading. And I imagine that in this 3-manifold, we have a framed link that projects to this picture. So that's local. That's a local picture of a link. And then we impose the relation that this link equals the following linear combination. So here's the same neighborhood. And here I consider a link which is the same as this one outside of the neighborhood, but inside it looks like this. And then we also take the other resolution, like this. So that's one. That's the main skein relation, and then there's one more, which is saying that if again we have a neighborhood like here, and then there's a link with a component that's just an unknot, an embedded unknot in the 3-manifold, then that can be replaced by the expression minus a squared plus a to the minus 2 times the link that we get by deleting this component. So those are the skein relations. This is a definition of the Kaufman bracket skein algebra. And I should mention here, because these are framed links, I should say what the framing is. So here, when I draw pictures like this, I assume that the framing points out of the blackboard. Okay, so that's the definition of the algebra. Now this is a noncommutative algebra, and what is important is that this is a quantization of the algebra of regular functions on the SL2 character variety. So what I mean, so let me state it here as a proposition, the skein algebra quantizes the character variety. It means if we specialize this variable a to a certain value, we recover the algebra of functions on this scheme. More precisely, if we take the skein algebra and we take the a goes to -1 limit, so we set a equal to -1, then you get a commutative algebra, which moreover is isomorphic to the algebra of regular functions. So that's what the skein algebra is. That's why it's important. Maybe I should also mention, because we deal with surfaces with boundary, there's a variant of this definition here. So let's again suppose that gamma 1 through gamma n are some loops. So now they're going to be loops in this 3-manifold, which are homotopic to boundary components. This is a little bit of a sloppy way to say it. I guess really I should say their projections on S are homotopic to boundary components. So given such loops, we'll now define the relative skein algebra as follows. So it'll be denoted like this, sk a lambda of S. And to get this, we take the skein algebra defined over there, that's ska of S. And remember that this is an algebra. By definition, it's an algebra over Laurent polynomials in A. So the first thing I'll do now is extend scalars to the ring of Laurent polynomials in A and some additional variables, lambda 1 through lambda n. So we have additional scalars now, and we're going to impose one more skein relation. So here I draw another one of these pictures, but now I'm looking at a neighborhood of some boundary component of the surface. Okay, so this is a boundary component, and I consider this this loop here, gamma I. So this is the ith boundary component, and I'll impose the relation that this element equals minus lambda I plus lambda I inverse times the element that we get by deleting this component. All right? So that's the relative version of the skein algebra. And in the same way that the usual Kaufman bracket skein algebra quantizes the character variety, we have the following statement. So this relative skein algebra, ska lambda of S, quantizes the relative character variety. Okay, so those are the basic objects that we're interested in. The skein, these are the skein algebras. Maybe I should say, what does this mean? So this means if I set A equal to -1, and I set lambda I, these variables, equal to non-zero complex numbers, then I recover the algebra of functions on here. So our goal in this work is to address the following conjecture. This is a conjecture of Thurston from 2014. So he had the idea that the skein algebra could have a categorification given by some monoidal category. And to be a little more precise, we can interpret the conjecture as follows. We can say the skein algebra is supposed to arise as the Grothendieck ring of some abelian or triangulated monoidal category. And you could try to approach this just starting with the definition and trying to invent some kind of category that does this. But here we're going to take a little bit different approach, which is based on the notion of a Coulomb branch. So this is something that first appeared in physics, but more recently there's been mathematical work on this topic by Braverman, Finkelberg, and Nakajima, giving a precise definition of this. So the data that we'll start with to talk about Coulomb branches is a group G, let's say this is a complex reductive algebraic group. And we'll let N be a complex representation of G. And then we'll talk about various things associated to these data. And also just a bit of notation here. I'll use the standard notation from geometric representation theory and write K for the field of formal Laurent series in a variable Z. And I'll write O for the ring of formal power series in Z. So given the group and representation like that, like this, I can state the following definition, which again appears in the work of Braverman, Finkelberg, and Nakajima. So we have this vector space N, and let's write N of K to mean N tensor with K, and also write N of O for N tensor with O. Then the first part of the definition is the following. We'll define a space. This one doesn't exactly have a name, but it's denoted T sub Gn in this paper. And it's defined like this. It's this kind of product here. So what do I mean by this? I mean, let's take the product first of the k points of G. So G is an algebraic group. We can make sense of its k points. We take the product with this space NO, and then we quotient by an action of O points of G. And the action is given as follows. So an element B acts on a pair G comma S by this formula. So B is an O point of G. G is a K point of G. And S is an element of N of O. So for those who have studied the affine-Grassmannian, you can see that, that this reduces to the definition of affine-Grassmannian when we take the representation to be the zero representation. So this is some very natural generalization of that. But the thing we're really interested in here is a subspace which is called the variety of triples, which is a little bit misleading because this is actually not a variety. This is an ind scheme, but don't worry too much about this for this talk. So this is a subspace of this T space, defined as follows. It's denoted RGN, and it consists of elements. So let me write brackets, bracket GS for the equivalence class of a pair GS in this T space. You consider such pairs for which G acting on S lives in N of O. So in general, if you act on S by a K point of G, you expect to get something in N of K, and so this is a condition that cuts out some kind of subspace of T. And maybe it's confusing because it's not obviously a variety of triples, but there's another different way I could define this where it would clearly be triples of data. That's where the name comes from. All right. Now, there are going to be some group actions on this space. Let me describe those. So we have this group G on the one hand, and let's suppose that we have another algebraic group F acting on this representation N. So we have an action of F on N, and if that commutes with the G action, then we will write G tilde for the product of G and F, and one can then define an action of the following group on the variety of triples. So there exists an action of O points of G tilde, semi-direct product C star on the variety of triples. So to get the action of O points of G, you use like the left multiplication on this T space, and then this C star is acting by loop rotation. So it's rescaling the variable Z in this definition. And okay, so one has an action like that, and I'll just mention here that these groups have some significance in quantum field theory in physics. So the G is what we would call the gauge group of the theory, and F is called the flavor symmetry group. Okay, so that's a space that we can construct from given some groups and a representation. And then we have the following fact, which is also essentially proved in the work of Braverman, Finkelberg, Nakajima. So they considered the following category. We take the bounded derived category which I'll denote D, So that's a bounded derived category of equivariant coherent sheaves. So we have this, again, we have this action on the variety of triples. And we look at coherent sheaves that are equivariant for that group action and take the derived category. And it's a little bit subtle to define this because, like I said, the space of triples is really not a variety. It's an in scheme, so one has to be a little bit careful here. But let's not bother with the technicalities. So so we get this category. This will be a triangulated category. This is the category of G tilde of O, semi-direct product, C star, equivariant, coherent sheaves on the Braverman, Finkelberg, Nakajima variety of triples. So what they showed in their paper is that this category has a monoidal product we'll denote this by the symbol star because this is what we call the convolution product on that category. So we have this triangulated monoidal category, and given such a thing, we can, of course, look at the associated Grothendieck group, which now has a ring structure, because we have this convolution product. And let me give a name to that. This is also from Braverman, Finkelberg, Nakajima. So you get the algebra with underlying vector space K0 of D. So we talk about we use the complexified Grothendieck group of the category. So that inherits a product from this monoidal structure on the category. And this algebra is called a quantized K-theoretic Coulomb branch. So that's a noncommutative algebra, and it's also a quantization of something. So meaning in some semi-classical limit, you recover a commutative algebra, which is what physicists would call the algebra of functions on the Coulomb branch. Okay, so now we've seen the definitions of two different algebras. And I can state yes? How many gradings do we have? I don't know. I mean, that's kind of a hard question to answer. There are natural gradings on this. Yes. What? Well, I don't know if I can answer that. Only one? I mean, who knows? Maybe you tell me what grading you're thinking of, and Yeah, this is not very obviously related to Grothendieck homology. I mean, certainly what I'm talking about here should eventually be related to that, but I don't know how to do that. And if you're thinking that this space is like the Grothendieck homology or something, then I would say no, that's not the point. Okay. Now, let me formulate the main result. So let's consider a quiver. Let's write Q for the quiver with underlying graph like this. So I'll draw some of the nodes, some of the vertices as squares and some of them as circles because these play different roles in our story. So we have some quiver of type AN here. And, well, maybe not of type AN, quiver of type A. So let me assume that the number of these circular vertices is n minus 1. So here you have n minus 1 vertices. And let's consider the following associated vector space. Let's write n for this space, which you could think of as like a space of representations of this quiver. So for every arrow, we consider linear maps from C2 to C2. So it's like you're taking a representation of this quiver where the dimension vector has all 2's at every vertex. That's our n. And now, if we write G for the set of gauge nodes, and by gauge nodes, I mean the ones that are illustrated as circles in the diagram, and write F for the set of framing nodes, which are the squares, then we get natural actions of the following groups on this vector space. So we have, first of all, the group G, which is the product of SL2 factors, where you have one factor for each gauge node. And then there's this F, which is defined as it's an algebraic torus, which is it's obtained by first of all taking a product of copies of C star, one for each arrow of the quiver. And then you also have factors associated to the framing nodes. So for each element of this F, we again have a one-dimensional torus, but now we'll view it as a group of matrices like this. So these are groups that have natural actions on this vector space. You can probably figure out yourself what the actions are on n. And so now we have all the ingredients we need to construct these categories, these monoidal categories, and the associated Coulomb branches. And we obtain the following result. So this is in our recent paper. We show that there exists a C algebra isomorphism from the relative skein algebra of a punctured sphere. So take the surface of genus 2 with some number of punctures. We show that that algebra is isomorphic to a quantized Coulomb branch. So it's isomorphic to the Grothendieck ring of some monoidal category. And so that provides some kind of an answer to the, some kind of solution to the conjecture of Thurston that I stated before. It gives you a categorification of the skein algebra, at least in this genus 0 case. And there are many other things that we would like to do with this. One of the main questions, one of the main kind of motivations for defining a categorification is to study canonical bases for these algebras. And indeed, these categories have been studied by others. So there's work of Sabancaudas and Harold Williams, which considers a monoidal or an abelian monoidal subcategory of this. So it's the heart of some T structure on the category. And they show that the simple objects in that category give you a canonical basis. So in future work, we hope to return to this and relate that basis to some of the known bases for skein algebras. Thank you very much.
Thank you very much. Questions?
Thanks. My first question is, could you say a bit about where the convolution product comes from?
Where does the convolution product come from? Yeah, so it would take a little bit of work to give the definition, but the idea is that one writes down a diagram in the category of in schemes involving this space, this variety of triples and other spaces, and then using operations like push forward and pull back.
So it's some sort of correspondence thing.
Yes. Yeah, so it induces a functor on the derived category, which is this convolution product.
I wanted to ask one more question.
Yes.
On the left-hand side, you have lowercase n. What does it translate to on the right-hand side?
The lowercase what?
N.
N.
Like S0 n plus 2. What does it translate to on the right-hand side? Because... Oh,
yeah,
okay,
it corresponds to the number of vertices of the quiver. Yeah.
Hey, thanks for the very nice talk. That was very nice. I want to ask about because we know the skein algebra, you take a certain limit and you get back to the moduli space of flat connections for Simons.
Yes.
And the reason that we get the skein algebra is to quantize it, right? Is to introduce the Fock-Rossley Poisson bracket and then blah blah blah. So I want to ask about for the category that we have, this derived coherent sheaves, which I don't really understand what that is.
Okay.
What is the Poisson structure?
Yeah, that is not so clear to me, I guess. Maybe it's known, but the way I think about the Poisson structure on this quantized Coulomb branch is Well, it's a quantum algebra, so you can take the commutator and then look at the expansion in the quantum parameter, and you see the Poisson bracket. But I don't know a more a geometric way to define it. There may be, that may be known, but I don't know.
What's the quantum parameter?
The quantum parameter.
Yeah.
Yeah, good question. So, so as I've defined it, this is just some algebra. It's an algebra over the C star equivariant K theory of a point. And it's a basic fact in K theory that this is isomorphic to Laurent polynomials in a variable Q.
Okay.
And then this Q is getting related to this A under the isomorphism.
Okay, I see. Okay, thanks.
Yeah.
There is also the grading. That grading is also related to this, because this is a triangulated category. Over there is a sheet. There is a grade. So can you repeat the question? I can't understand. Yeah, I mean, since you are talking about the triangulated category.
Yeah.
And there is a grading.
You mean like homological grading?
No, the shift.
The shift, yeah.
Yeah. That grading is it related to this Q or not?
Yes, it is.
Yeah.
Yes.
Another question is that I want to know that what happens when this parameter is a sixth root of unity.
Is a sixth root of unity?
Yeah.
So,
No, the lambda or something, the delay.
Yeah, we don't require any restrictions on the values of these parameters. So you can set it equal to any non-zero complex number. We consider any non-zero complex number. So not just you know, we don't exclude roots of unity or anything like that. And I'm not aware of anything in particular that happens if you take a sixth root of unity, but
the relation becomes the root becomes trivial.
the what becomes trivial?
Because there's a spine relation, and when you move out the circle,
yeah,
there is a parameter coming out.
yeah.
And six, that parameter becomes one.
Okay.
So
I don't know. So I'll say one thing, which is the skein algebra does acquire a larger center when the parameter is a root of unity. But other than that, I don't know what happens when you choose special values of these parameters.
Okay, I want to ask about some intuition behind your main result. Is there any intuition or algorithm for constructing the quiver from the surface?
Yes. Right.
Can you explain a little bit?
So this is something that basically has already appeared in the physics literature. So there is a construction due to Gaiato, which takes a Pants decomposition of a Riemann surface and produces a quantum field theory. And at least in this genus zero case, one can construct a quiver like this that defines the theory, and this is just lifted directly from that paper.
So you use pairs of Pants decomposition and then doing some gluing procedure to get the quiver?
Yeah, the quiver is defined by a Pants decomposition. But I should say that this is not possible for a general Pants decomposition of a general surface. So if I took a higher genus surface, I wouldn't be able to write down a quiver. They talk about something called a generalized quiver, and this lies, I think, kind of outside the framework of Braverman, Finkelberg, Nakajima. That's why we restrict here to the genus zero case.
Okay, I see. Thank you.
Okay. So let's thank the speaker once again.
Thank you.